Zach Woodard?
Yes.
All right. Stephen Turner. Jesse Martin. Different Jory. Oh, you're right, Kirk? Yeah, I got something for you. A couple. Kyle Kohler. Jesus. Megan Walker. Another Jeremy Reitkirk. Derek Heineman. Anthony Lee. Deja McClellan. Brandon Simpson. Oops, excuse me. Matt Letney. Jimmy Flood. Val Peterson. Chris Macklin. Here's Jory Owens. Jacob Childers. Travis Black. Joey Najira. Michael Bach here. Michael Bach. And John Caldwell. Jory Owens. And Jory Owens. And Jory Owens. You're making up some points, huh? All right. Megan Walker, still not here. Carter Dewberry. Jory Owens. Carter Dewberry. What's your name? I've got something for you in here. I'll find you again. Derek Heineman. Megan Walker still not here. Jory, Megan, Zach Woodard. Oh, yeah. You go, Jory. Zach, Anthony Lee, Jory Owens, Carter Dewberry, Jimmy, Jesus, Jesse Martins, John Caldwell, Jacob Hoffman, Matt Letney, no Matt Letney, Anthony Lee, Kyle Kohler. What's your name? Jacob? Which one? Sanchez. Kyle Kohler. There you go. Derek Heineman. Jacob Childers. John Caldwell. Jared Robertson. Go. Here's Jesus. Derek Heineman again. Derek Heineman. And Jeremy Reitkirk. Jeremy Wright. This is Jeremy right here, correct?
Yes, sir.
And Jesse Martin. Jesse Martin. Jacob Hoffman. Jacob Hoffman. That's you. Yeah. Jacob Hoffman.
I've already done catching up.
Matt Letney. Jacob Childers.
He's in college elementary.
Jacob Childers. Oh, you. Two here. And they're both in. Jacob Childers, Travis Black. Oh, there's two here. Joey Najira. Flood. Well, the stack's getting small enough I can hold it without cramping my hand. Jesus. Deja. Anthony, Michael DeBach, Carlos Aguilar. Is that you?
Yes, sir.
Saru. Anthony Lee, Jacob Hoffman.
Back there. No, he's in the back talking.
Jacob Hoffman. There he goes. Just got to pronounce it right. Is that it? There you go. Zach Woodard. Mike Letney. Mike Letney. Kyle Kohler here yet? You are? Okay. Aha. Okay. Kyle Kohler. Hold your hand up. There you go. Jory Owens. Excuse me. Pardon my reach. Stephen Turner. Stephen Turner. Stephen Turner, Stephen Turner, Stephen Turner, Stephen Turner, Stephen Turner, Stephen Turner, and Stephen Turner. Booyah. All right. Does anyone have any questions about homework assignments they would like to address? Hey, this came up, one of you, in the homework assignment, and specifically the ambiguous case when we're dealing with the law of sines. So let's look at this. I'm going to for the law of sines, if you know two sides and one angle, but that angle is not included between the two sides you know, you use the law of sines to solve for that triangle. But it's what's called the ambiguous case. In this case, we've got one side that's known. I think they call that one B. Yeah. You know side A and you know side B. Side C is unknown angle A is known and angle C is unknown. Now, because you know side B and A, you know the height between this apex and the base C is going to be H. And that's equal to B times the sine of angle A. All right? Now, one possibility is that A is less than, the side A, the length of it, is less than B times the sine of the angle A, or is it less than H? If this is true, then there is no solution, because it simply can't reach the base. Doesn't matter what angle you swing it at through, it cannot reach the base. It can't reach side C if it's too short. There is no triangle that you can make with those two sides and that angle. Now, another possibility is that A is greater than B. Okay, now if A is greater than B, greater than or equal to B, then there is only one solution. I'm not really sure that's true. Yeah, if A is longer than B, you could swing it way over here, or you could swing it over here. I guess they're saying both of those would be the same triangle, just mirrored. Okay, that makes sense. Sorry, people, I didn't mean to throw a red herring at you. I was just questioning the textbook. The reason it's now the ambiguous case is, when is it possible to have two solutions? Oh yeah, there's one other case. If A is equal to B sine A, then there is one and only one solution, and it's a right triangle. If this side is just this length, then that's the only solution, the right triangle. But when A is greater than H, B sine A, but it is also less than B. So when B is greater than A and A is greater than H, then there will be two possible solutions. This solution and this solution. Does everyone see that? Now, of course, as A gets longer and longer until it equals B, then it passes and you're only going to get the one solution. Either way, mirrored one way or the other. So, how can we organize these better? no solution. A is less than B sine A.
One and two, or the two and three are basically the same, because A is greater than or equal to B is only one solution, basically repeating that in the third one.
B sine A is H. That's not the same thing.
Right.
B sine A is not.
Right. Okay.
No, that's not the same thing. But you get one solution if A is greater than or equal to B. Of course, seems to me, yeah. Or if A is exactly equal to H, which is equal to B times the sine of A. Finally, you get two solutions if B is greater than A, but A is greater than B sine A, or H. Does that help sort this out for you? So you can put it in a table and make that comparison whenever you're. Now all you got to remember is that this is for the case when you know two sides and one angle that's not included between them. In which case A is the one opposite the known angle. A is the side opposite your known angle, and B is the side that joins them.
The book has it set up like in the previous questions.
Which question are we looking at?
Well, just the other ones like 12 and 9. They have them set up differently. Like they have A where you have the B, and then they have B where you have the A. So I just want to make sure that when you're trying to find either a no solution, one solution, or two solutions, it really doesn't matter how you have the triangle set up.
Right. A is the, regardless of how it's labeled in that picture, A is the opposite, is the side opposite from the known angle, and B is the side that connects the known angle to the other known to the side A. Okay. Now, if you know two sides and one angle, but it's between the two sides you know, then you can't use law of sines. You're going to have to use law of cosines. Okay. So yeah, they're going to. So I found out. Remember, we found out last class period. They'll start labeling everything one way with A on bottom, B on one side, C on the other, and then 2 pages later they swap you all around. So just what you need to remember is that the known side is opposite the angle. B is the side that connects them. So whether they label it, this angle is always going to be labeled the uppercase of the other known side, because that is a standard that they adhere to in order for the law of sines to work. So you can relabel them as you need to in order to solve the equation, solve the problem. Does anyone have any more questions about from the homework? Okay, little overview. We got today and tomorrow and then spring break. So How many of you still have homework assignments that you've yet to turn in? That are due, that are past due? You need to get them to me by tomorrow. Okay? Make your points. Now, we're in week 11 right now. So week 11 homework is due Monday when we come back from spring break. It's not due yet. So, why, have you already done it? You can turn it in. Don't let them give you grief about overachieving either. What I want to impress upon you is that after tomorrow, late homework I will still accept, but I will only grade it if I get time. That means when we come back and your week 11 homework is due, not Monday, it'll be Tuesday because that's when we meet. If you don't turn in week 11 on Tuesday when we come back, it'll be late when you turn it in on Wednesday, and it'll go into the late stack, and it will get graded if and only if I get a chance. Now, I'm going to try to get everybody's work graded and get all the points to you that I can. But I have to start being practical to make sure that I meet my deadlines for turning in grades. Okay, so if you've got an exam that you missed and you need to do a makeup exam, get with me today or tomorrow. If you can't, I will try to work with you when we come back from spring break, but it will be as time allows. For the record, if you've taken an exam and you did not like your score, you do not get a do-over. Okay? Doing a makeup exam is not doing a retake exam. They're two different things. Now, I am dropping the low score, so if you've got the one grade, that one test that's just dragging you down, it will go away, and it should already be reflected as such in your scores, in your grades on Canvas. But what I want to make sure each of you understand is right now it's showing you a grade based on the work that you have done and turned in. And if you have late assignments that you have not taken, that you've not turned in, at the end of the semester, all of those assignments that you did not turn in, they turn into zeros. And that is going to kill your grade. So get those homework assignments turned in. Get the points. Yes? It means that one test does not count toward your grade. No, it's whichever test you scored, whatever grade you have that is the lowest grade in your grade, on your transcript, that grade will get thrown out and not counted towards your final grade. What's your name? Matt? Oh, bless your heart. I got about a whole stack of papers to give to you. Here we go. Let's see. Everybody think about your homework problems that you're working on. See if you come up with any questions while I sort through this stack again. Matt Letney? Do you have any homework assignments that you've not turned in yet? Okay, well, you need to get them turned in by tomorrow. Yeah. Is that one or two sheets? What was the second one? Oh, they're both yours? Okay, good. Yeah, I'm going to be a very happy camper when Joey Najera or Stephen Turner shows up. I'm going to be happy to see Anthony Lee, too. You came in? Oh. Please make sure I didn't give you someone else's. Has anyone not signed in? Okay, Anthony Lee. One. You're bet. Anybody else came in that's hiding in my stack of papers here? All right. And nobody's come up with any. Y'all did 2 of these for me? Thank you. No, I don't think so. Well, that was yesterday, and we didn't meet yesterday, so whoever wrote that wrote the wrong date.
I did it because I got my information from somebody else.
Today's Pi Day. How did you not know that? Who doesn't understand that today is Pi Day?
What is today's date anyway?
3/14.
Oh.
March 14th.
I thought it was the 13th. That doesn't really matter. Besides that, 3.14 is actually
It's close enough. What's the difference between 100 and 100 plus 1?
1.
The difference is 100. 100 plus 1 is still 100 until and unless you can measure the difference. All right. Well, how about if I give a shot at regaining control of the class?
We don't build buildings like that.
Yeah. Oh, actually, you most definitely do. I promise you, you do not cut.
They'd be sloped because they're that long.
Well, that depends on how big that one is, doesn't it?
That's true. What's your unit of measurement?
If we're dealing in nanometers, I bet you can't tell the difference.
Nope.
All right. Any more questions before we start on law of cosines? Nope. All right. Before I go through and I derive the law of cosines for you, I need to make sure you understand something. If we have 2 points on a coordinate plane, how do you calculate the distance between them? Does anybody know? Well, let's turn it into a right triangle. And what do we know about the coordinates of this point? We know that its x coordinate is x2, and we know that its y coordinate is y1. So, what's the distance between from here to here? It's x2 minus x1. And the distance from here to here is y2 minus y1. That means that for any 2 arbitrary points, we can always calculate the distance between them using Pythagorean's theorem. Okay? Does everyone see how I get this? D squared is equal to a squared plus b squared, where a is equal to x2 minus x1, and b is equal to y2 minus y1. Okay? Any questions about this? Because I'm about to use this very same principle, this very same technique to derive the law of cosines, and if you don't understand what I'm doing when I do it, it might lose you. All right? So I'm going to leave that there for the moment. Now, to derive the law of cosines, I'm going to make a couple of fortuitous choices. There's my coordinate axes. And here is the origin. Now, I'm going to lay down one side along the x-axis. What does that mean? Now this is side B that is, we know it's B, the length of it is B. So what does that tell us about this coordinate? The coordinate of this endpoint. It's at x equals B and y equals 0. So its coordinate is B0. Now, I'm going to take side A, I'm going to put it here. Now that means this is going to be side C, so that's angle C. This is going to be angle A, and this is going to be angle B. Okay? With side C over here. Everybody with me so far? Now, what do we know? Think back to our trigonometric functions. What do we know about the coordinates of this point right here? What is the x coordinate of that point? Nope. No. Think of your definitions. What is sine? Well, let's just do sine of theta. Y divided by radius. What is cosine theta? X divided by radius. Well, in this circle, A is my radius. So, the coordinates of this point, the X coordinate is A times cosine of C, and the Y coordinate is A times the sine of C. Everybody with me? That is the X and Y coordinates of this point. Now, I want to point out to you something here. And this is a side note. We're not going to divert from what we're doing. But this is true whether this angle C is acute or even if it were obtuse. This point here would still be A cosine C, A sine C. No matter what this angle C is, those are always going to be the coordinates for the endpoint of side A. All right? Take that distraction down, and we'll continue. Now, what we need to know is this distance. Oh, almost got it. We need to know the length of side C. Well, we know both the endpoints of side C. We know the X and Y coordinates of this endpoint of C, and we know the X and Y coordinates of this side of C. So, we know that 2 points in a coordinate plane, we can calculate the distance between them. It's going to be, and I'm going to erase this for you now. We're going to have C squared is equal to B minus A cosine C squared plus 0 minus A sine C squared. Did I get that right? That. Got it. Okay. Does everyone see how we got this? How I got this? Everybody look up at it. I want eye contact. Let me know that you're with me so far. Okay. Well, we can do the squaring, and hopefully I wrote it down the same way they did in the book, so I don't have to do that by hand. B minus A cosine C, yep. Well, if I square this, when I get B squared minus 2AB cosine, right? Yeah, 2AB cosine C plus oh yeah, in the last term, a squared cosine squared c. That takes care of this squared. Now this squared is just, that's 0 minus, so it's just minus a sine c squared. It becomes plus a squared sine squared c. This is all equal to c squared. Everybody still with me? Well, I can factor out an a squared right here, and that becomes a squared times cosine squared c plus sine squared c. Just last week, what is that identity? Sine squared plus cosine squared equals 1 squared. So this is just a 1. Or reordering it, we get side c squared is equal to b squared plus a squared minus 2ab cosine c. Now, I did that for one side. I think it should be kind of obvious we could repeat the same procedure for the other two sides. And when we do, we end up with b squared is equal to c squared plus a squared minus 2ac cosine b. Get that right? And finally, a squared is equal to c squared plus b squared minus 2bc cosine a. Well, I hope I got that one right. I turned them around, but yeah. Those are the three equations that make up the law of cosines. Say again?
So the cosine part's going to be harder than the sine.
You'd be surprised. Because with the law of sines, we had all that complication about the ambiguous case. Oh, but I only had to do that to show you how to derive it, to show you where the law of cosines comes from. You don't have to do the factoring and stuff to use it. You don't have to start with here and go to there to get here. We've developed it and we've shown that this is true in the general case. And so now we just use the law of sines and cosines. In point of fact, because of that little complication with the ambiguous case, as a general rule, you will usually find it preferable to start working with the law of cosines when you can. Now, of course, it depends on what you know. What are the knowns that are given to you? And is there a way to state that succinctly? There are, everybody pay attention, let's do some questioning and answering. Let's do some thinking about this. There are 6 elements that define a triangle. There are 3 sides and 3 angles. And we know the angles have to add to 180. So if we ever know two angles, we know the third. Okay? If you know 3 of the 6 elements, you can almost always solve the rest of the problem. Why did I say almost? Who can tell me the one time when you can know 3 of the 6 elements of a triangle and still not be able to nail it down to any one but to an infinite number of solutions? Say again? Bingo. When you know all 3 angles, then you can pick any side and you can have an infinite number of triangles with those 3 angles, because all of the sides can vary to maintain those 3 angles. So let's modify our statement a little bit. If you know at least 3 things about a triangle, and at least one of those things is the length of one side, then you can solve for the rest of it. You can solve for a triangle. Unless somebody, when can you still know 3 things, at least one of which is a side, but not be able to nail down one well-defined triangle? When you are using the law of sines and you have the ambiguous case. That means if you know 2 sides and 1 angle, and that is not the angle between the 2 sides you know, then you have the ambiguous case. And you may have no solutions, you may have 1 solution, or you may have 2 solutions. But even then, that's the only 3 choices you get. You're not going to end up with an infinite number of solutions. Okay? What happens if you have 2 sides and 1 angle, but that angle is included between the 2 sides? Yeah, we'll go ahead and use their example so I don't have to do arithmetic. There we go. Um, 283. We know 2 sides and 1 angle, but it is the angle that is subtended between the 2 known sides. This is when you would not use the law of sines. In order to solve this triangle, you would need the law of cosines. And I got another marker that's dying on me, so thank you, whoever picked that one up. How would we use the law of cosines to solve this triangle? Say again? We would start calculating c squared. It's going to be equal to a squared plus b squared minus 2 times 3 times the cosine of 60 degrees. What's the cosine of 60 degrees? Isn't that 1/2? Don't one of you dare trust me on that. Somebody punch it in a calculator. It is? It's 1/2? Okay. So it's 4 plus 9 minus 6 times 2 is 12 times 1/2. Or 13 plus 6 is what? 13 minus 6. That'd be 7. Okay. Yeah, I did say plus, didn't I? It's minus. See, I told you not to trust me to do arithmetic in my head. So it's c squared is equal to 7. That makes c equal to the square root of 7. Now, we know all 3 sides, and we know one of the angles. If we can figure out one other angle, we got it beat, because we know, once we know the one of the other two angles, we can find the third angle just by subtracting them from 180. How would you find this one now that we know that all 3 sides in one angle? A lot of people would be tempted to go back and use the law of sines, because the law of sines just looks easier to use. It's just ratios equal to ratios. And you got to do like actual arithmetic to do. Yeah. Well, they don't work it out as an example, but they will point out to you that if you use the law of sines, you end up with an equation that can have 2 solutions. And it does kind of tie back to that whole ambiguous case thing. So if you do, then you're going to have to sort out which of the 2 solutions is going to be true. Simpler approach is just continue using the law of cosines. You use the law of cosines, now you can write the same equation for either one of the other 2 side angles. What angle do we want to solve for? A? Okay, then we need 2 squared is equal to square root of 7 squared plus 3 squared minus 2 times the square root of 7 times 3 times the cosine of A, right? So, did I get that right? Okay. Let me give myself some more room to work here. Now you can work out whatever kind of memory aid will help you remember which sides work together. It's basically whichever side you're solving for, that's the it's the opposite angle that you're going to be using. So we've got 2 squared minus 7 plus 9. Nope, sorry. 2 squared, we got 4 minus 7 minus 9 is equal to minus 2 times the square root of 7 times 3 times the cosine of A. What's 4 minus 7 minus 9? Somebody. Negative 12 equals negative 6 times the square root of 7 times cosine A. So 12 over 6 times the square root of 7 is equal to cosine A. Does everybody see where the negative signs went? When I divided a negative by a negative, it became a positive. Or 2 over the square root of 7, because 12 over 6 is 2, is equal to the cosine of A. And if you put in 2 divided by the square root of 7 and take the inverse cosine, what angle do you get? $49.1 degrees, right? 40.9. There we go. The arithmetic is a little more involved, but the answers will be more straightforward. You're not going to run into near the difficulty, the ambiguity that you can run into using the law of sines. Anybody got any questions yet? Like I was saying, you can use whatever mnemonic memory aid will help you remember how to organize those. But my advice is make sure they're written down on your index card, because that's my best memory aid, is having it written down. Okay. How many of you are ready for spring break? And how many of you are ready to crank out the last of those homework assignments and get them turned in? Except for the one guy that's already ahead of the class. They've already done, you know. We are coming up after spring break. We're going to come back and we're going to do chapter 4.4, which is finding the area of a triangle. Yeah, not really very complicated, I know. We're going to introduce something called the law of Heron that gets a little involved. Anybody heard of that before? No? Heron of Alexandria, back ancient Egypt. Yeah, well, he came up with a rule for finding the area of a triangle. It's kind of cool, but don't worry about it yet. We'll get to it when we come back. You're not going to worry about it one little tiny bit, huh? Well, when we do come back, we're going to cover that. And then we are going to start reviewing everything that we've covered since the last exam. Because the next week we're going to have an exam. And it's going to cover all of this material. So, who would like to start reviewing some of the material we've covered so far right now? What have we covered so far?
That's what we did.
So did you say the exam that we're going to be taking is
No,
last exam that we just had.
Right.
Okay, so it's basically just going to be over the law of sines, law of cosines, and the area.
The law of sines, law of cosines, the area of a triangle, which will include the law of Heron. So start remembering that name now, even if you don't know what it means. No, we come back will be week 12 of our semester when we come back. That's when the assignment for this week, 11, will be due on that Tuesday when we come to class. Remember, when we come back, late homework gets put in a late pile and only gets graded if I get to it. And I will grade the most recent, the least late homework first when I do have time. So, the first week we're gonna cover the area of the triangle that first day, and then we're gonna do review on the Thursday of week 12, and the next exam will be the Tuesday of week 13. Which will be the next week after that. Now, surely somebody has had questions or troubles with some of the homework. And now it's a really, really good time to start looking at those. Something that confused you or that you didn't quite understand why you did it. Sure. You got one out of the homework you'd like to do, or just use one out of the book? Just use another example. Number 11? Sure. Actually, here's a good one to do right here. We'll do number 11 too. Which one is number 11? Yeah, I know, it's 11, right? Yeah, we'll look at 11, but here, let's look at this first. Let's do this example where we've solved the different permutations of one angle and two sides and two angles and one side. Let's look at what happens when we know all three sides. Because if you know all three sides, then you know that you're not going to run into any ambiguity. Yeah, they give us 3, 4, and 6. Page 284. So we know A is equal to 4, B is equal to 3, and C is equal to 6. So how do we find these angles? Well, pick a side, any side. Let's start with 6 squared. That would be C squared equals A squared plus B squared minus 2AB cosine C, which in this case is C is 6, so this is 36, is equal to 16 plus 9 minus 2 times 4 times 3 times the cosine of C. Or, let's see, that's 12 times 2 is 24. So we got 16 plus 9 is what, 25? Minus 12 times 2 is 24 times the cosine of C. So 36 minus 25 is 11. Sooner or later, you people are going to learn to trusting me to do arithmetic in my head. Somebody break out a calculator. 36 minus 25. It's 11. So we have 11 is equal minus 24 cosine C. So negative 11 over 24. Why?
Oh, we started out with fun. Never mind. I thought 11 was
Nope. No, it's 36 minus 25 is still positive. Yeah. So what's negative 11 over 24? Take an inverse cosine. $117.28. Anyone want to confirm that?
Can you explain why you subtracted 36 minus 25? We got the 11.
I did. I had 36 was equal to 25 minus 24 cosine C. So I subtract 25 from both sides.
Oh, okay.
And that leaves minus 24 cosine C on this side and 36 minus 25 on this side. Did anyone else confirm? Because we know what happens when he runs a calculator. Yeah, no, this one is definitely going to be. Yeah. It should definitely be greater than 90. It's going to be an obtuse angle. $117.28 degrees. So we now have C is equal to 117.28 degrees. Yeah. Now we just need one more. Yep. Now, I guess this time we'll do, let's look for angle A. So we'll write 4 squared is equal to 3 squared plus 6 squared minus 2 times 3 times 6 times the cosine of A. Or 16 equals 9 plus 36 minus 2 times 3, 6 times 6 is 36, cosine A. (16 minus 9). Okay, yeah. No, 9 plus 36 is 45, right? 45 minus 36 cosine A is equal to 16. 16 minus 45 gives us, not even going to try to do that one. Negative 29 is equal to negative 36 cosine A. So 29 over 36, divide by the negative, positive, equals cosine A, and that points to A equals Did you already do it? 36.34. Okay, now everybody trust but verify. And I get 36.34 degrees as well. Now, which one of these do we use to find the third angle? Exactly. Once you know two angles, you know the third. Who else got that? Boy, if we ain't some steely-eyed calculator jockeys, huh? Look. Now, who was it wanted to do one of the homework problems? 11? 12? All right, let's set it up. Y'all are going to have to be quick on those calculators because we only got a few minutes. So we've got a slightly obtuse triangle. Hmm. 11 is 95 on my book. What page are you on? 286. Okay. All right, so we've got A equals 2, B equals 3, C is unknown, A is unknown, B is unknown, and C is 95 degrees. We know two sides and the included angle between them, so we have no choice but to use the law of cosines. So let's start with C squared equals 2 squared plus 3 squared minus 2 times 3 times the cosine of angle C, which is 95 degrees. What's the cosine of 95 degrees? Times 3 is 6, times 3 is 12, times cosine of 95? Okay, times 12 and subtract it from 13. And when you subtract a negative, you're actually going to be adding them. This is 12.91. All right. So this is 13 minus minus a negative 1.046. Or 14.04 is c squared. And if we take the square root, we get c is equal to 3.75. Now all we got to do is fill out one of the other, do one of the other angles. So we can write 2 squared is equal to 3 squared plus 3.75 squared minus 2 times 3 times 3.75 times the cosine of, forget which one I was working on now, A. All right. So 4 equals 9 plus 14.04 minus 6 times 3.75, 22.5 cosine A, or 4 minus 9 minus 14.04 equals minus 19.04 is equal to minus 22.5 cosine A, or divide both sides by negative 22.5 and we get 0.846. 2 repeating is equal to cosine A. Take the inverse cosine, and A equals 32.2 degrees. And now you just subtract that plus 95 from 180 to get B. Any questions? Then I will see y'all. I'll probably see some of you between today and tomorrow turning in homework, but the rest of you I'll see when we get back from spring break. Thank you.
Thank you.
You have a good day.
Alright, that's late and that's today's.
Sounds good. Thank you. Oh boy. Yay. Thank you, Michael. Thank you. You need to speak up in class more.
Can I do my test now? My exam?
Oh, you didn't do exam 3.
Yes.
You absolutely may. That's not graded. Boom. Let's go down to my office. Uh,